Now we're going to talk about Newton's laws, example problems, with pulleys and friction. I actually want to start though by defining something called normal force for you. And normal force, I write that as a capital F with the subscript of a capital N. Slightly different than your book, but this is the symbol I use for normal force. And the normal force has the SI unit of the Newton. And the normal force is basically defined as your force that is perpendicular to two surfaces in contact. So for example, here's the ground, and I have some sort of crate resting on the ground. The two surfaces in contact are where the crate and the ground touch. Perpendicular to that then is where the normal force is. So the normal force in this problem is perpendicular to where the crate and the floor are touching. Another example is, say that we have a ride. You walk into this ride and there's it's a circular room, and the room starts to rotate and go around and round and round in circles. And you're standing in the room, and then the floor lowers. But the room is rotating, so you are, in essence, you are pinned up against the wall. So here's you pinned up against the wall as the room rotates. So where is the two surfaces in contact? Well, it's where your back is up against the wall. Therefore, the normal force, which would be perpendicular to that in this case, would be in this direction. A little bit later in the year, we'll explain why that normal force is pointing to the right as opposed to the left. But for right now, I want you to understand that the normal force is perpendicular to the two surfaces in contact. All right, let's talk about our first example problem with pulleys. So I have some sort of table. Attached to the table is a pulley. We have some sort of block on the table with a rope attached to that block, which then goes over the pulley, and there's some other hanging mass hanging from the pulley. We'll call the block on the table, we'll call that block 1, and the block hanging off of the pulley, or the mass hanging off the pulley, that's mass 2. So the first thing we want to do is draw a free body diagram on each object. So on object 1, we have the weight acting down, M sub 1G. We have a normal force acting upward, F sub N. And we have a force of tension pulling to the right from the rope. On mass 2, we have the weight of the mass, M sub 2G, and we have a force of tension pulling upward from the rope. Now Newton's third law of motion says that these forces of tension on object 1, here, this force of tension here on object 1, and the force of tension on object 2 are equal in magnitude and opposite in direction. So if we know the value for the tension, say, acting on object 1, then we know the value for tension on object 2. And now that we've drawn free body diagrams, we can use Newton's second law of motion to add up all the forces acting on each individual object. First thing we must do before we add up the forces is we need to assign direction. So let's make right positive, and why don't we also make up positive plus y. And let's go ahead and sum up the forces in the x direction on object 1. So on object 1, the forces in the x direction, there is only one, and it is the force of tension. It's positive because your block is moving to the right. Let's say, actually I forgot to define that. Let's say that block 1 has a movement or a speed moving to the right, or a velocity right. So because of that, then the force of tension should be pulling to the right, and that's the only force in the x direction, and then that's going to be equal to the mass of object 1 multiplied by the acceleration of object 1. Let's go ahead now and sum up the forces in the y direction for object 2. Now there are only forces in the y direction on object 2, so that we will not be summing up forces in the x direction on object 2. But in the y direction, again, we have a force of tension which is acting up, so that's positive. Minus, we have a weight here, m sub 2g, and it's equal to the mass of the second object multiplied by its acceleration. Now, when you look at object 2, it should be accelerating downward, so we're going to give that a negative a. What's interesting about these acceleration values, the one in object 1 and the one for object 2, is the magnitude is the same. The direction may be different, but the magnitude is the same. And so we can use the fact that the magnitudes are the same to combine these two formulas if we want to later on. Now, let's say that in this particular problem we want to find T. So let's say I asked you, what is the tension between the two blocks? And let's also say that I gave you the mass of object 1. Let's say I said it was 1.0 kilograms. And let's say I gave you the mass of object 2. Let's say that was 2.0 kilograms. If we look at our formulas, let's look at the first one here for the sum of the x direction for object 1. I have an unknown here, which is tension. I have the mass, which is good, but I have another unknown, which is the acceleration. I don't have that acceleration. If I look at object 2, the formula for object 2, I see again I don't have tension. I do have the mass of the second object, which is 2 kilograms. I know G. We could probably, let's round that to 10 today. I have the mass again of the second object, but I don't know A. So basically, so I don't know A. So A I don't know. That's supposed to be a question mark there. T I don't know. A I don't know. And T I don't know. That is two unknowns. And if we have two formulas, we can find two unknowns. And we happen to have two formulas. So let's rewrite those formulas. I'm going to, let's see if I can make more room here by lifting this up. Oh, good, I can. So let's rewrite that. The sum of the forces on object 1 in the x direction was tension is equal to m1a. And the force in the y direction for object 2 was tension minus m2g is equal to m2 times a negative a. So what we're going to do here is apply substitution. So I want to find tension. So let's see, what can I do here to find tension? What I can do is rewrite the sum of the forces in the x direction for object 1 and rewrite that for acceleration. So if I rewrite this equation, I would get the acceleration is equal to the tension over the mass of object 1. And then what I'm going to do is take that expression for acceleration and plug that in my second formula. So that my new formula now looks like, let's write that, the tension minus m2g equals m sub 2 multiplied by a negative tension over m. Now we just need to rearrange this equation and solve for T. So with a little bit of mathematics, we'll go ahead and solve for T. I forgot my little subscript on my m sub 1 there. First thing I'm going to do is subtract T on both sides. Rewriting this, negative m sub 2g is equal to, let's write this as negative T multiplied by m2 over m1 minus T. I'm going to go ahead and factor out a T. So that's going to give me negative m sub 2 over m1 minus 1. The left side is negative m sub 2g. Then I'll go ahead and divide both sides by this quantity. of negative m sub 2 over m1 minus 1. Again, negative m sub 2 over m sub 1 minus 1. And now I have an expression for tension. So let's plug in our numbers for tension here. I'm going to have a negative, see my mass of the second object was 2.0. My g value, let's call it 10. I want the 10 to be two significant figures, so I can put a line over that 0. All over, I have a negative, let's see, 2.0 for the second mass over 1.0 for the first, minus, let's make this a 1.0 for my 1 value, so that my answer, I want my answer to come out to be 2 sig figs. That's why I want everything in 2 sig figs. And the answer comes out to be 6.7, that's rounded to two significant figures. And the unit is going to be newtons because we were solving for tension. All right, let's talk about another example with a pulley. And this time we're just going to draw the free body diagram. I have a pulley here. I have some sort of a rope on either side. I have some mass hanging on the right side. And on the left side, I have some sort of a bucket. And I have a person in the bucket. They're leaning over. And they're pulling on this rope here. And here's the person. Here's their head. They're happy, but they're pulling down on this mass here. Okay, so what's the free body diagram on here? Well, on the left side, we have the mass of the bucket. Maybe we'll call the person object 1, the bucket on the left object 2, and the mass on the right object 3. So on the left, we have the mass of the person that is felt in the bucket plus the mass of the bucket multiplied by g. So that's the weight on the left side. We also have the force of tension acting upward on the rope that's holding the person there. And on the right side, we have the weight of object 3, m sub 3g. We also have the force that the person is applying. They're pulling down as they pull down. And then we have the same force of tension acting upward because of Newton's third law of motion. Let's go ahead and say that the person is pulling themselves upward. So we have an acceleration. Well, let's say they're pulling themselves upward at a constant velocity. So my acceleration value then, I'm trying to see where I'm going to write that. My acceleration value will be 0 because they're pulling themselves up at a constant velocity. And let's go ahead and make upward positive. So just real quick, if we were to apply Newton's second law of motion on this, let's talk about the sum of the forces acting on objects 1 and 2. That would be the tension, which is upward, minus their mass, m1 plus m2, multiplied by g. And that would be equal to their mass, the mass of the person in the bucket, times their acceleration. Of course, their acceleration is 0, so that whole thing is equal to 0. And that was the sum of the forces of object 1 and 2. The sum of the forces of object 3 would be the tension acting upward minus the force of the pull of the person minus m3g, and that would be equal to m3a. Again, that acceleration value is 0, so the sum of all the forces acting on object 3 would be 0. Okay, now I want to talk with you about friction. So friction, or small f, in newtons is equal to the normal force, your F sub n, multiplied by something called mu, and it's a Greek letter mu, which stands for the coefficient of friction. Okay, so the small f is your friction in newtons. The F sub n is your normal force in newtons. And your Greek letter mu stands for the coefficient of friction, which has no unit. And the coefficient of friction just basically tells you how rough the two surfaces in contact are. So the friction happens between two surfaces. Your coefficient of friction tells you how rough those two surfaces are. Now, friction always acts opposite to motion. To make it less, just apply lubricant like lotion. There are two types of friction we need to know in this class. One is called kinetic friction, or F sub k. This is the friction of motion. The other type of friction is called static friction, and this is friction between two objects when they are not moving. All right, let's draw a free body diagram with friction. So here's the ground. We have some crate sitting on the ground. Someone or something is applying a force or pushing this crate. There is a weight to the crate, or mg. There is a normal force upward. If the crate were to move because of the push to the right, it would move to the right. So there is a force of friction opposite to that. If the crate is not moving, we say we have a static frictional force between the crate and the floor. And my question to you is, what is the force required to get the crate to start to move? If I make right positive, I sum up the forces in the x direction. My push minus my static frictional force is equal to the mass of the crate multiplied by the crate's acceleration. If the crate is not moving, then the acceleration is 0, and so my pushing force is equal to my static frictional force. If I want to get the crate to start to move, then I must apply a pushing force that is greater than my static frictional force. Now, what if my crate is moving? I still have a weight, I still have a normal force, there's something pushing it to make it move. Let's say it's moving, there's a constant velocity to the right. My frictional force must be to the left. We give it a subscript of k for kinetic frictional force. Let's make right positive. And my push minus my kinetic frictional force is equal to the mass of the object multiplied by the object's acceleration. It's moving at a constant velocity, so my acceleration times my mass is 0. So my pushing force is equal to my kinetic frictional force, which is equal to the normal force of the object multiplied by the coefficient of kinetic friction. Now recall, if you're on a level plane, your normal force and your weight can be the same. So this is also equal to the mass of the block multiplied by the acceleration due to gravity multiplied by the coefficient of kinetic friction. If we looked at a graph of force versus time, of someone pushing on a crate that is not moving, and then we want to get it to start to move and then move at a constant velocity, what we see is as time goes on, you apply a force, increase your force, increase your force, increase your force, the object actually starts to move, and then we get a lowering amount of force required to keep the object moving at a constant velocity as time goes on. So this part, the very peak here, represents the force required to start to move, and the horizontal line here represents the force required to keep the object moving.